In this lecture, we're going to start a new topic, Laplace transforms and their applications. Now, this particular presentation can be thought of as very introductory, right? We're going to define the Laplace transform, we're going to calculate a few, and then we're going to see how we can use tables to help us. Now, the whole thing driving our study of Laplace transforms is actually the last topic, differential equations. Now, Laplace transforms were formed originally by a French mathematician called Laplace to solve linear ODEs with constant coefficients. And you might think, well, I already know how to solve those by, method of undetermined coefficients or variation of constants maybe. Well, one of the big advantages with Laplace transforms in the ODE environment is that the calculations can be simplified greatly. Okay, usually when you solve an ODE, you form some general solution, then you incorporate the initial conditions. Laplace transforms cuts out the second step. Okay, so it can be used to simplify many of the calculations involving ODEs, especially higher ODEs, where say you've got a fourth order problem and you've got four initial conditions. So the idea with this particular presentation is just the first two topics. So we'll discuss the Laplace transform and calculate some. Okay, well, as I'm sure you're all aware, many problems in our world involve systems that are acted on by discontinuous or impulsive forcing terms. Now, the differential equations that we use to model these processes, they can be a little bit awkward to solve by the classical methods that we've learnt, such as the method of undetermined coefficients and the method of variation of parameters, variation of constants. So in this section, we're going to learn a new approach based on the idea of an integral transform. In particular, we're going to look at a special transform called the Laplace transform. So what is a Laplace transform? Well, suppose I've got a function, f of t. Think of t as time if you like. This is how we denote and define the Laplace transform of a function, say, little f of t. Okay. You can see that we use this curly L. So the curly L means the Laplace transform of what's in the curly brackets. Now let's just move over here for a second. Essentially what I'm doing is I'm taking my original function f of t, I'm multiplying it through by an exponential, and I'm forming this improper integral with respect to t. Now if you look closely in here, you'll see, okay, I'm integrating here with respect to t. But I've also got another variable in there, s. So actually, this whole thing really defines a function of s. Okay, so there's a couple of ways we can write the Laplace transform. This way, and no matter which way we write it, this is actually what it represents. Okay, now it's common in the realm of Laplace transforms to let the lowercase letters be functions of t and uppercase letters, capital letters, to denote the original function's transform. So if I had a function little g of t, big G of s would represent the Laplace transform of little g. Okay, so whenever you see capital letters in the context of this presentation, you would think, oh, that's just the Laplace transform of little f. Now note also that this is an improper integral. And we know from, say, a first course in calculus that improper integrals can be a bit tricky because sometimes they converge and sometimes they don't converge. So when we speak of the Laplace transform with this improper integral, we're, I guess we're tacitly assuming that this is only useful for when the integral converges. Okay. Now you may not have this down here. You don't really need this definition. I'm going to draw a picture that explains everything. Okay. Now I've just sort of put that that bottom bit down just for completeness, but you don't need to know it. Now, what I guess a good question here is, what kinds of functions will we be dealing with? What kinds of little f make that previous improper integral converge? Okay, what kinds of little f make this improper integral converge? Well, we're going to look at the following kinds of functions. A piecewise continuous function and a function that satisfies this inequality for t sufficiently large. So think of this as a function that grows. So f here is a function that grows at most exponentially. Now what do I mean by a piecewise continuous function? Well, here's a formal definition here, but I can just as easily draw a piecewise continuous function. Okay? Suppose this is my interval of interest. I'm going to draw a piecewise continuous function. Okay? That's an example of a piecewise continuous function. What I can do is, just from this picture, split up the interval of interest into a finite number of subintervals such that on each of those little subintervals the function's continuous. Okay, the function is continuous on each little open subinterval. And as we approach the endpoints of each subinterval, f approaches a finite limit. The f doesn't go off to positive infinity or negative infinity or something like that. Now, it's not essential that f be defined at the endpoints of the original interval or any endpoints of our subintervals. Okay? So that's essentially a picture of a piecewise continuous function. Now, if I have time, what I'll do is I'll actually come back and show why this ensures the Laplace transform integral definition converges. But if I don't have time, then it's not a huge thing. Okay, so let's actually compute some Laplace transforms. Now, throughout our investigation, we're going to assume that all the functions we're dealing with and taking the transforms of satisfy this condition. Okay, and this condition is not a restrictive condition. There's lots of functions that satisfy this. Okay, so this is not a massive barrier to computing Laplace transforms. Okay. So let's just get a feel for these Laplace transforms and let's calculate some. Now a little bit later I'll show you how to use a table for this, but it's important to still be aware of how to calculate these things from a first principles point of view. So suppose I've got this exponential function where a is a constant, little a. We're asked to compute the Laplace transform. Okay, well, we're going to use this definition directly and just replace f of t with this function here. So we use 1 directly. Now, actually having the knowledge of this Laplace transform opens up lots of doors, and it gives us lots of other transforms. Okay, so this is not an isolated case with limited applicability. Knowing the Laplace transform of this actually is going to open up lots of doors for us. Okay, so let's go back to our transform from 1. We're going to replace f of t with e to the minus at in there. And then I'm going to see if I can integrate. Okay, so what I can do is just do a little bit of work on the integrand. Come up with the following. And what I would like to do is just integrate. I can do that. Now, if I wanted to be very careful, what I would do is the following. I would write this improper integral as the following limit. So as b goes to infinity, it's just the following. Okay, so I do the integral first, and then I'll take the limit. If that limit exists, then we say the integral converges. Okay, so let's do the integration. So we're integrating with respect to t here. So we treat s and a as a constant. And we're going to get something like this. Okay, so plugging in t equals b and t equals 0, I'm going to get the following. Okay, when t equals b, I'll get something like this. And when t equals 0, I'm going to get e to the 0, which is just 1. And all I've got to do now is take the limit. Now, here, we're only considering the case where s is strictly greater than a. Okay, so it means that this exponent will be negative. All right, so as b goes to infinity, this is going to go to 0. Okay, so the Laplace transform of this exponential e to the minus at is 1 on s plus a. All right, well, what can we do with that kind of information? Well, what happens if a equals 0 here? What function do I get? I'll get 1, right? E to 0, just a constant function. So if a equals 0, then f of t equals e to 0, which is 1. So if I replace a with 0 in here, I get the Laplace transform of 1 straight away. It's 1 on s. Okay, that's pretty good. We didn't have to do any integration. So we've calculated 2 transforms now, a general exponential and, as a special case, the Laplace transform of 1, just a constant function. Well, we're not quite done yet. Let's have a look at this exponential down here where I is just from complex numbers, right? So it satisfies I squared equals negative 1. So if I replace, say, minus a with IB, I can work out the transform of this. So let's go to the transform, replace A with, we'll replace A with negative IB. So it's going to be something like this. Now that doesn't look too useful, but what we can do is multiply through by the conjugate. And see if it simplifies. Okay, well, when I expand this bottom bracket, I'm going to get something like s squared plus b squared. Now, if I break this up into real and imaginary parts, I can come up with the following. By the way, the b here is independent of the b in these calculations. Okay, so the Laplace transform of e to the ibt, where b is a constant, is given down here. Now, can anyone suggest how might that help us get other transforms? Yeah, so what do you think that the Laplace transform of cosine bt would be? Can you see it? Or sine bt, just from that bottom line? Well, we know that e to the ibt is cos bt plus I sine bt. So maybe I can use that to form Laplace transforms for other trig functions. So we'll come back to this in a second. So here's an example involving cosine bt. Compute the Laplace transform. Well, we're actually, I'm going to show you two ways to do it. You can use this, or you can just use another sort of a similar approach. So I'll show you two ways of doing it. Now we know from complex numbers that we learned in first year, I can write cosine bt as e to the ibt plus e to the minus ibt all over 2. Now, what I can do is use what I've just calculated here and take the Laplace transform and hopefully come up with the transform for cosine bt. So now, because the Laplace transform only involves integrals, it's a linear operator. So I can actually break this up and bring the half out the front. Sorry, let me break that up. Okay. And well, I've calculated that on the previous slide, and I can easily calculate that just by replacing b with minus b. So I'll get something like the following. So just from the previous slide, okay, so that is the Laplace transform of this. And if I replace b with minus b, I'll get this. So you can see cancel, cancel, and the so that is the Laplace transform of cosine bt. That's one way of doing it. Now, of course, if you wanted to, you could just put cosine bt in here and then integrate. But can anyone see why that wouldn't be optimal? You can do it, but why isn't it very fun to integrate an exponential times cosine? No, it's the integral is still defined, okay, no problem. Yeah, you've got to use integration by parts. So my view with these kind of calculations is you want to avoid integration by parts as much as possible, okay? So using these other ideas and employing, say, this exponential function can save you a lot of time, okay? If you can avoid integration by parts, you should, okay? So that's another way of doing it, using integration by parts. But let me show you another way of doing this. Let me show you another way of doing this. And we're going to use this thing down here. Okay, now I know, again, from first year, Euler's formula, e to the I bt equals cosine bt plus I sine bt. So let's take the Laplace transform of both sides. Now taking the Laplace transform of these two, again, because we're using integrals, this Laplace transform can be used as, can be thought of as a linear operator, right? So I can break up the Laplace transform of the whole of this. And I can bring that I out the front. So I times this transform. Okay? Now if we look back to the previous slide, the Laplace transform of e to the I bt was this plus I times this. So what we can do now is just equate the real and the imaginary parts. Right? So the real part is this, and that's the real part of that. So these two things must be equal. And if we equate the complex part, that and that have also got to be equal. So we get what we wanted. So equating the real and imaginary parts, we obtain the Laplace transform of cosine bt. And as a nice little bonus, we get the Laplace transform of sine bt. Okay, so with these kinds of problems, you want to work smarter, not harder. And hopefully I've convinced you that just knowing one or two basic transforms can save you a lot of time. In particular, you can avoid integration by parts in a lot of cases. All right. So here's a good question. Again, we want to work smarter, not harder with this one. You may have seen this question somewhere before. The Laplace transform of this function is given here. Apply Leibniz rule by differentiating under the integral sign to show that the Laplace transform of t times little f of t is this. Hence, compute the Laplace transform of t times e to the minus at. I think in your notes I've got plus at here, so just make sure that you've got the minus sign, just to be consistent. Okay, it doesn't really matter if you have a minus or a plus there. Okay, it still works. Okay, so assuming we can differentiate under the integral sign, let's differentiate with respect to s, and come up with the following. So we'll get something like this. Now, Leibniz rule says I just take the DDS, move it inside, and change it to a partial derivative, because inside I've got a function of t and s. Okay, so we're differentiating partially with respect to s in here, so we imagine all the t's are constant. So what's going to happen, the exponential is going to be differentiated and the minus t will come to the front. Okay, now if I just sort of bring the minus sign at the front and rearrange the integrand, I'll get the following. So let's call that star. E to the minus st times tf of t. Now this is just with a minus sign at the front and tf of t instead of just f of t. So it is so this then is this. So if I just bring the minus sign around, I'll get star. Now that looks very pretty, but the last part of the question is an application of that identity. How is it useful? How can it save you time? Okay, well, let's look at the alternative just for a second. Okay, so they say hence compute the Laplace transform of t e to the minus at. Well, let's say you did that by using 1 directly. You would have t times an exponential that you'd have to integrate. Again, you have to do integration by parts. Okay? With this, you can avoid it. So how do we do it? Well, we're going to use this. Right? So in this setup, f of t would be e to the minus at. And what this says is that the Laplace transform of tft equals the negative of the derivative of the Laplace transform of little f of t. So for this application, what I want to do is calculate the transform of this, then differentiate it, and then just put a minus sign out the front. Okay? Okay, so we know that the Laplace transform of this was just calculated over here. Okay, so but to use this, what we want to do is take that and differentiate it. So differentiate it with respect to s, so it's going to be something like this. So using star, essentially the Laplace transform of this is just the negative of this. Okay, so again, no integration necessary. No integration necessary. Now some of you may be thinking, well, how do I remember that? Well, you don't need to. You don't need to remember star. Okay? Because it will be given to you in some form of a table, usually. Okay, so here's a general independent learning exercise. See if you can prove this. Anyone have any idea how you would prove this bottom part here? F of n in brackets means the nth order derivative of big F. Any ideas? How would you prove that bottom bit? I'll tell you what, have a think about it. See if anyone can get it in the break. Oh, reduction formula? Yeah, maybe. Yeah, not. Well, you want to avoid integration. So, what do we do up here? We differentiate it. So if you keep on differentiating, just keep on applying Leibniz rule again and again and again, maybe that'll help. Okay, so that's a few of the ideas on how we calculate Laplace transforms. Now, to complement our Laplace transforms, we define the inverse Laplace transform. So instead of this curly L, you have L with this -1, or L inverse. Now, it's defined through the following identity. So you can think of L inverse as just undoing the Laplace transform. So, you know, let me sort of expand on this a little bit. So if I take the transform and then take the inverse, they cancel each other out. And similarly, if I take the transform of the inverse, it cancels out. Okay, so think of the inverse Laplace transform as undoing or retransforming. Now, we've already seen that big L, or curly L, the Laplace transform, is a linear operator because it involves an integral. Now, L inverse is also a linear operator. So what does that mean? Well, it means that I can distribute through these brackets, right? Where here alpha and beta are just constants. F1 and F2 are suitable functions. So if I, for example, how is this useful? Well, if I wanted to calculate the transform of this function, e to the minus 2t plus cosine t, then it's just the sum of the two transforms. Okay, so from a computational point of view, it's important because I can just go through and calculate all the individual transforms and then add them all up. Now, you might think, well, what's the form of the inverse Laplace transform? Well, it does have a general form, but it requires a knowledge of the theory of functions of complex variables. So we're not going to look at the explicit representation. Okay, so for our purposes, just think of the inverse Laplace transform as undoing the Laplace transform. Okay. Now, we're going to use tables quite a lot to calculate transforms and their inverses. Now, as we've seen, the Laplace transform can be sometimes quickly calculated by integration or other methods, but a real need for a table arises when calculating the inverse transforms, because we don't have an explicit way of calculating inverse transforms from a definition, an explicit representation, if you like. It's like knowing differentiation without knowing integration, or vice versa. Sort of have to guess and check a bit. So what we do is we use a table of integrals to help us out. Now, in this table of integrals, there's a couple of special functions. This is the gamma function here. You might have heard of the gamma function. If n's a positive integer, then there's a relationship between gamma of n plus 1 and n factorial. And this u of t is the Heaviside step function. Okay, it's a discontinuous function with a step, a sort of unit jump. So let me give you a picture of this, right? So this then is a picture of this unit step function, this Heaviside function. It's 0 to the left of t equals 0. It's 1 to the right of t equals 0. And at t equals 0, it's 1/2. So it's like the average of the jump. Now, some textbooks define it slightly differently at this jump point. Okay, it's not a big deal. For example, you could define this step function as just being 0 here or 1 here, or not even defined when t equals 0. So having that little jump point and its definition is not essential. It's not super important. Okay, so the table that I'm going to work with in lectures is the following. Now, I must admit, in your assessment, you won't get quite such a wide table. Okay, so you need to be aware of what transforms you'll be given in the usual formula sheets with all the exams. So down the left-hand side, I've got functions of t, and down the right-hand side, I've got their transforms, functions of s. Okay, now there's a few things down here that look a little bit strange. And actually, some of those transforms are theorems, like the first shifting theorem, the second shifting theorem, and so on. So don't worry too much about that for now. What we're going to do is just get a little bit of experimentation going with using the table. Okay, so let's have a look at the following simple example. Here I've got a function of s. I want to use a table to calculate the inverse transform. Okay, so using the linearity of the inverse transform, I can write it like this. Now I can sort of reduce that 9 to a 3 squared. So if I go to my table, what I want to do is look down the right-hand column and find something like that. I want to look down the right-hand column and find something like that. Okay? So if we look down, I can go right, no. Okay, there it is, something like that. 1 on s plus a is a general form of this. So 1 on s plus 4 is that, just with a equals 4. Then look across to the left-hand column to find the inverse transform. Okay, in this case, a is positive 4, so the inverse transform of that will be e to the minus 4t. Okay, so let's move on to that one. I want to look down the table to find something like s on s squared minus 3 squared. Gosh, yes. So if I look down here, I see something like that. B is going to be 3. So I look across. The inverse transform of that is going to be cosh of 3t. Now, whenever you're using these tables, it's always good to say that you're actually using a table. Okay, that way if you're doing an examination, the person that's looking at your assessment knows, okay, well, they've used a table. They just haven't sort of, copied from the person next to them or something. Oh, sorry, cosh 3t. Okay. So let's do a couple of other ones. That was pretty easy. For example, let's say I wanted to calculate the inverse of 1 on s minus 1. Okay, so I look down my table till I get to something like 1 on s minus 1. Well, it'll be that with a equals -1, I look over here, it'll be something like e to the t. Okay, what about some other ones? The inverse transform of 1 on s squared, let's say. Okay, so I look down, if I look down to the second row, I've got the inverse transform of 1 on s squared, which is just t. Okay, what about, say, the inverse transform of 3 on s to the 7? Okay, well, I want to look down the table, the right-hand side, till I get something involving, say, 1 on s to the 7. Well, if I look down, that is almost like it with m equals 6. But notice I've got this m factorial up the top, so I have to do a little bit of adjusting there. So if I, say, bring that 3 to the front, I can form the following, just by dividing and multiplying by 6 factorial. Okay, so this part now is contained in my table down here with m equals 6. So I look across, it's going to be t to the inverse transform is going to be t to the power 6. So 3 on 6 factorial, that's going to be something like 1 on 120. I've left off a factor of 2 here. Okay, so this should be 240, not 120. Okay, 240, not 120, sorry. Calculate the Laplace transform of t cosine t. And you might think, oh, hang on, I can't do that. Well, if you look down the table, do I see t cosine t anywhere? No, but I have that. I have tg of t. The transform of that is just minus g prime of s, where big G is the transform of little g. So using the table of transforms, I can come up with the following. The Laplace transform of cosine t, well, let's see if I can find that. Yeah, so the Laplace transform of cosine t is going to be s on s squared plus 1. So to compute the Laplace transform of this, I differentiate this and stick a minus sign in there. So if I differentiate, say using the quotient rule, I should get the following. And so a minus of that is the transform of this. So it's going to be s squared minus 1 all over s squared plus 1 squared. Okay, so you can see how using a table can sometimes greatly simplify the situation. You don't need to remember too many of these identities.